So, hello guys, let's start in like 10 minutes so that a few others can join the session. It's like 6 p.m. right now, so we'll start at 6 around 6:10. Let's wait for a few others. Okay, so I guess since I believe no one else is joining, so I guess we can start the session. So first of all, welcoming again everyone. So this is our sixth session for the NPTEL Discrete Maths Problem Solving course, the problem solving session. And in this session, we'll be talking about mostly mathematical induction and pigeonhole principle and stuff like that. So I once again I'd be assuming that you guys have gone through the lectures and we'll focus more on problem solving. And yeah, I guess we can just start the session now. I have a bunch of problems prepared. I'll just share my screen and we can start discussing. Uh, because of the weather, the network quality might be bad today. So if you guys ever feel my voice is breaking or anything, just inform me via chat and I'll try to again speak the sentence. Okay, so I hope my screen is visible to everyone. So we can get started. Uh, the first question says that there are n people in a town having the length of their name greater than 3. So we are given n people in a town, all of whom have length of their name greater than 3. Then we need to find out what is the number of people in the town such that we are guaranteed to find at least 2 people with the same second alphabet in their name. So, and there are n people with the number of alphabets in their name greater than 3, how many minimum number of people should we pick so that at least 2 people have same second alphabet in their name? Just to write down what is given to us. N people with greater than 3 alphabets in name. And what we need to find is the number of people such that at least 2 people have the same second alphabet. Any guesses? Would anyone like to guess the answer for this in the chat? More or less, all the questions today will be of this flavor only, where we'll need to apply pigeonhole principle. Uh, so this is a good warm-up exercise, I believe. Let's just see. I think also we need to find the minimum number of people, not just number of people, because number of people can be large. Okay, maybe we should get started. Uh, So we know that there are n people given to us with the length of their name greater than 3, but we'll figure out that this n does not actually matter to us. The answer will still remain the same. So why is it the case? Maybe I should just say something like this. So the second alphabet, so we'll be assuming that everyone's name like does not, no one's name contains any special characters or any numbers. Everyone's name consists of only alphabets. The second alphabet in the name has 26 choices effectively, which are A to Z. Right? There are 26 alphabets. So the second alphabet can have 26 choices. So in the worst case, these 26 choices, suppose we pick some 26 people. Like it is not up to us to choose what 26 people are picked. We just need to ensure that whoever picks, if someone picks like 26 people, or like if someone picks the X number of people what is required, we always get at least 2 people with the same second alphabet. Let's say the correct answer to this is X, then we want to find that if even if an adversary picks X number of people, even then we should have at least 2 people with the same second alphabet. It is not up to us to choose the people. It is up to adversary. So this is an important distinction, because if it was up to us, then maybe we could have just chosen two people who we just saw that they have the same second alphabet, and we could have outputted the answer as two. But it is not up to us. It is up to the adversary to choose the people. So adversary will always try to choose the maximum number of people which don't have the same second alphabet, right? The second alphabet in general has 26 choices. What does this mean? As soon as we pick 26 people, let's say, which have first person has the alphabet A in the as the second alphabet. The second alphabet of the second person's name is B. Third person's is C. Till 26th person is Z. So in the end, the 27th person, which we pick, 27th person will have a repeated alphabet, because even if we pick the first 26 choices such that all of these are distinct, the 27th will still be one out of this A to Z, right? And then this will be a repeated choice. So effectively, by pigeonhole principle, I hope everyone understands what pigeonhole principle is. Pigeonhole principle just says that if there are n holes and n plus one pigeons, then there will be at least one hole with two pigeons in there. And this has been discussed in the lectures also. So yeah. 27th person will have a repeated alphabet. By Pigeonhole principle, if we pick 27 different people, we are sure to get at least two people with the same second alphabet. You can think of these alphabets A to Z as the buckets, and as soon as we pick 27 people, at least one bucket will contain two people. That's why we need to pick 27 different people. And note that so we have obtained that we need to pick 27 different people, but we also need to show that what is the minimum number of people. What we actually needed to find was what's the minimum number of people which we need to pick. Right now, what we have done is we have shown that if we pick 27 people, at least two people will have the same second alphabet. But we also need to show that this is the minimum number possible. That if someone picks, let's say, 26 different people, there will exist a case where the alphabets won't be repeated. We need to, so I hope everyone understands this. So we need to show, for showing the minimality of this 27, we need to show an upper bound, which we have shown that 27 is an upper bound. Like with 27, we will definitely have a solution. But we also need to show that if the number of people is less than 27, then we won't have a solution. So effectively, to show that 27 is the smallest possible, 27 is the smallest possible number. We need to show that less than 27 people can have different second alphabets. So we need to create an instance in which if we pick, let's say, 26 people, then they will have different alphabets. And this is also easy to show because we can just assume that there are 26 people who have, like, first person has the alphabet A, second has B, third has C, till the 26th person has Z. So this set of 26 people will always have distinct second alphabets. So 26 is not possible, and we have shown that 27 is possible. So 27 is the minimum possible number. I hope everyone understands this. For 26 people, we can have an instance where all the people have different second alphabet A to Z. So 26 is not possible. And we showed that 27 will always be possible. Hence, 27 is the 27 is the answer for us. Okay, so Akansha had written in the chat that is it 27. So yes, Akansha, your answer was correct. That there should be 27 people. So good job. Now we can move on to the second question, I guess. I hope this is clear. So note that one thing just I wanted to point out that this is very important whenever we need to show minimum number of people. How do we guarantee that something is minimum? Here in this argument, we have just shown that if we pick 27 people, then we will always have two people with the same second alphabet. But to ensure that this is minimum, we need to show that less than this is not possible. And for that, we gave this sort of argument. The argument is for the minimum number possible. So both of these arguments are important in general. I hope everyone appreciates this, what I'm trying to say. Now let's move on to the second question. Second question says that given a set of integers from 51 to 250, effectively the set of integers given to us is 51, 52 to 250. What is the least number of integers that can be selected such that any two of the chosen integers are consecutive? We need to, how many minimum number of uh, integers should we choose such that any two of the chosen integers uh, will be. So similar to last question, here we need to check consecutive integers. In previous question, we need to check the same alphabet. So let's just check. So 51 to 250, how many numbers are there? There are 200 numbers. And we can have a set of 100 numbers, which, so what I'm trying to do is let us divide this 51 to 250 into two sets, the odd numbers and the even number, 51, 53, 55, and so on till 199. How many numbers will this be? This will be just 100 numbers. And similarly, let us see this pair 52, 54, 56, and so on till 200. This will also have 100 numbers. And note that what's the special property of these 100 numbers? These are even, these are odd, and these are even. But with respect to this question, these 100 numbers have the property that no two of them are consecutive. 100 numbers such that they don't have any consecutive pair. Maybe I should write this. 100 numbers without any consecutive pairs. Similarly, we have another 100 numbers without any consecutive pair. So like what we are trying to show here, like here we showed that if we have 26 people, we can always have an example where these 26 have different second alphabet. Similarly, here we have an example where we can choose 100 numbers which won't contain any consecutive pair. So and so in the first example, in this first set also there are no consecutive. In the second set also there are no consecutive. So effectively what we have shown is 100 will never be the correct answer. Like we need more than 100 people. We at least need more than 100 numbers to ensure this sort of guarantee. We know that 100 is not possible. But we also, so this is the lower bound, like at least we know that 100 is the lower bound, that 100 or less than 100 is not possible. But we also need to show that an upper bound also, like what is the actually the least number of people. So what we'll actually be showing is 101 to be the correct answer. And what's the reasoning behind it? What I'm trying to say is, what we'll actually arrive at is that if we choose 101 integers, then we will always be guaranteed that uh, two of the they have though a pair is consecutive in those 100. Like there exists a consecutive pair in 100 and in a set of 101 integers. What I'm saying is these 100 numbers don't have any consecutive pairs. These 100 don't have any consecutive pairs. But as soon as we add, let's consider this set. As soon as I add another number to this set, let's say I add one more number. Let's say I add 54 or let's say 52. Then 51, 52 will indeed form a consecutive pair, or 52, 53 will indeed form a consecutive pair. So the intuition behind it is that after 100 numbers, if I pick another one, then I will actually be getting. If I pick another number, any of the above two sets, then we will get a. So this is all. I'm just trying to give you an intuition. This was a lower bound that 100 is not possible, and now we'll show that 101 is possible. But before getting to that 101, I'm trying to give you an intuition of why is the answer 101. This is because if I pick any more number in this set, then we will actually be getting a consecutive pair. So 100. So yeah, maybe I should not write it right now. This is more of an intuitive idea. And now how do we actually prove that 101 would actually be correct? So we can just divide the buckets in the pigeonhole principle, we take some buckets, right? And fill it with objects. So take the buckets as 51 to 52, 53 to 54, 55 to 56, and so on till 199 to 200. Okay, I think I wrote less. This should be 249, this should be 250. Similarly, this should be 249 till 250. So we see that these are 100 buckets. And as soon as I pick, let's say 101 numbers, suppose I was given these 100 buckets. These 100 buckets, how did I form these 100 buckets? I got an intuitive idea from these sorts of sets. That these are 100, these are 100. So maybe I can use these to form 100 buckets. As soon as I pick 101 elements, at least one of this bucket will contain two elements, right? If I pick 100 numbers, 51, 53, 55 till 249, then every bucket contains exactly one number. But as soon as I pick one more number, I pick, let's say 101 numbers and there are only 100 buckets, then by pigeonhole principle, I can say that at least one bucket will have two numbers. And if any of the bucket has two numbers, then those two numbers are consecutive because every bucket just contains two numbers and those are consecutive numbers. So let's say if the 101st number filled this bucket 55 to 56, then I would have obtained that 55, 56 is a consecutive pair. So I hope everyone gets the idea of what I'm trying to say here. So if we pick 101 numbers, then at least two numbers are guaranteed to belong to one bucket. Or maybe I should write better. If we 101 numbers, then there exists a bucket containing two numbers. Something like this would be better. And why is this? Because of pigeonhole principle. Because 100 buckets, 101 numbers, so one bucket should contain two numbers. And PHP, like PHP denotes PHP short form for pigeonhole principle. And because of this, reloading. Hence, the two elements of that bucket will be consecutive. Right. So we have actually shown that if we pick 101 numbers, then we are guaranteed that there will always be a consecutive pair. And we have also shown that if we pick 100 numbers, then there exists a case where there won't be any consecutive pair. So 101 is actually the minimum possible. Hence, 101 is the minimum possible minimum number of integers in right. I hope everyone is able to understand this idea. If so, then maybe we can move on to the next question. Next question is again based on induction answer. So next third question says, which of the following statements is false? We are given a bunch of statements and we have to identify which of these are false statements. So the part A says that Pn is equal to nq minus n is divisible by 3 or all n belong to Z. So Z denotes the set of integers. So we have to show the like, is the statement true or false that Pn equals to nq minus n is divisible by 3? Here you can go option by option. What do you guys think? Is this true? That nq minus n is divisible by 3? So maybe I should just tell you guys that, yeah, it is actually true. And why is this true? Because we can see it this way, that we can write nq minus, we can factorize nq minus n as this. And so from nq minus n will come out and it will be n square minus 1 inside. And n square minus 1 can be written as n minus 1 times n plus 1. This is just basic high school maths. We are just factorizing this expression. So we know that nq minus n has three factors, n, n minus 1, and n plus 1. And note that n is an integer. So we actually have three consecutive integers of whom nq minus n is a product. So nq minus n can always be written as a product of three consecutive integers. And note that so if there are three consecutive integers, then at least one of those should be divisible by 3. Right? Because if first one is not divisible by 3, like let's say this is of the form 3k, n is of the form 3k plus 1, like let's say n minus 1 is of the form 3k plus 1, then n will be of the form 3k plus 2, and n plus 1 will be of the form 3k plus 3, which will again be divisible by 3. So in all the cases, like it is easy to see that for given, if we are given k consecutive integers, even not just 3, then one of those integers will be divisible by k. And exactly one will be divisible, not more than one. Because two consecutive multiples of k will have a separation of at least k between them. I hope everyone is able to follow what I'm trying to say here. Since the factors are three consecutive integers, at least one of the factors will be divisible by 3. And this can be somewhat generalized that if there are k consecutive integers, then one of the integers will be divisible by k. This 3 can be replaced even by a k also. So note that if one of the factors is divisible by 3, then the whole number is also divisible by 3. And that's why we get that this statement is true. The option A is true. Now let's move on to option B. Option B says n square is greater than 2n plus 1 for all n belonging to z plus. And z plus is the set of basically positive integers. So z plus denotes the, let's just assume that z plus denotes the set of natural numbers. So do you guys think that this is true? Is this statement true for n belonging to z plus? Is n square greater than 2n plus 1? This should be easy to do, guys. This part. Is this true or not? Yes, exactly. So good job, Akanksha. So it can be easily shown that this is false for n equals to 1. So this is false because for n equals to 1, uh, this statement, this inequality, let's say, does not hold. And even for n equals to 2, this will not hold. You can see like n equals to 2 gives 4 and this side gives 5. So even for n equals to 1 and n equals to 2, both for both of these ends, this is not true. But you can see that for n equal to 3, this will become 9 and this will just be 7. So for n equal to 3, this is true. So maybe this inequality does not hold for n equal to 1 comma 2, but it might be possible that it holds for like, so we know that this statement is false, like it does not hold for all n because n for n equal to 1 comma 2, this does not hold. But just for our practice, or let's say for your purposes, you can try it yourself. That you should try this yourself, that prove that this inequality holds for n greater than or equal to 3. So it does not hold for n equal to 1 comma 2, but actually it can be proved that n square is greater than 2n plus 1 for n greater than or equal to 3 actually. So you should try this yourself, and I'll give you a hint just that this will be like you can try later on after this session. You should use induction to prove this. So assume that base case would be n equal to 3. For n equal to 3, this is true. Then assume that this is true for any n. Then you need to show that this is true for n plus 1 also. So something like that. I hope everyone is familiar with induction. Okay, so we know that option B is false. Now coming to option C. Option C says that Pi is equal to 1 plus 3 plus 5 till 2i minus 1. So this summation, 1 plus 3 plus 5 till 2i minus 1, is actually equal to I square for all I belonging to z plus, where again z plus is the set of positive integers. Let's just assume that natural numbers. So if z is the set of natural numbers, this z plus like the z plus is just the set of natural numbers. So we need to effectively show that 1 plus 3 plus 5 till 2i minus 1 is I square holds true for natural numbers or not. Let's just try to put in small values of I. So if we put I equal to 1, we will get on the left side, this sum will be only equal to 1 because 2i minus 1 will be equal to 1 and right side will also be 1. Similarly, if we put I equals to 2, this side will just be 1 plus 3, the left side. So it will be equal to 4. And similarly, I square will also be equal to 4. Similarly, you can obtain that for it holds for I equal to 3, 4, 5, and so on also. So it seems that this inequality is true. This equality, this equation is holds true, and yeah, it actually is true. But like for proving, like we have, as I have discussed a lot of times in the past also, for disproving something, you just need to give an counter example. Like in option B, we had to just give a counter example for disproving. But in option A, we had to give a proof for proving something. Similarly, in option C also, since we have to say that the statement is actually true, we have to prove this, so we will need to give a proof. And how should we prove this? It can actually be proved easily using induction. Can be proved easily using induction. So one thing you should keep in mind that this principle of mathematical induction is actually a very powerful tool, and it helps us prove a lot of stuff. So this uh, you should keep in mind is very important in all of computer science, even in general mathematics. So yeah. And so the inductive claim will again be something like in this that pi is 1 plus 3 plus 5 till 2i minus 1 is I square. Base case holds for I equals to 1. And then if it holds for I, uh, then it holds for I plus 1 also. You need to show that. Then option D says that n is less than 2 to the n for all n belonging to Z. So if we need to show that is this true or is this false? I think this is also quite straightforward. That one thing to note here just is that here n is not z plus. Like in these options, we had z plus, z plus. Here n is just z, so it is a set of all integers. Even negative integers are present in this claim. So for all, if we are to show for all integers, does this claim hold true? That n is less than 2 to the n for all n belonging to Z. Okay. Would anyone like to point out in chat? What do you guys think? Does this hold true for all integers, positive, negative, any integer? Yes. So Akansha has said that it's true. So yeah, actually, Akansha, this is true. And suppose this was true, then yeah, it actually holds true. So I can even tell you guys that this holds true. But one thing to note here is again, if something is true, we need to prove that it is true. We just can't say that it is true. We need to actually prove it also. And the technique which I described you guys earlier, that it can be proved easily using induction, like induction can be used to prove the previous cases. But in this case, there's actually a catch. In option D, there's a catch. That n is for all possible integers. So n is uh, not just positive integers, but n contains negative integers also. So if we have the domain as a set of all integers, then applying induction exactly can be a bit troublesome, right? Because if n was only positive integers, then we could have inducted and took the base case as 0. And assuming base case 0 holds true, we would have shown that 1 holds, p of 2 holds, p of 3 holds, and so on. But if n belongs to the set of all possible integers, then uh, the minimum possible case, like the base case, will be something minus infinity, which is actually not a finite number. So you can't just argue a base case, in that setting. If if the domain of n is unbounded on both the ends, then you'll need to be a bit more clever. You can't just apply induction directly. In these cases, we had that there was like the n was bounded at least on one end. At one end, n was bounded by the value, even though in other end it was unbounded and went to infinity. But in this case, like it goes in both directions, minus infinity and infinity. So we can't just apply induction like blindly black box in the black box setting. We'll need to be a bit more clever. And how can we be a bit clever in this setting? Actually, we can just see that maybe we can just see that if n is negative, then this side is less than 0. So if n is negative, then this side is less than 0, whereas 2 to the power, a negative, even a negative number will be greater than 0. Like 2 to the power minus 1 is only equal to 1 by 2, which is anyways greater than 0. So if n was negative, then this inequality holds. Like we did not even need to use an inductive argument. If n was negative, then we could have just straight away said by the fact that this side is negative and this side is positive. And now the remaining part is that we need to show n is less than 2 to the power n only for positive values of n. And now we have made n bounded at one side. Now n is bounded at one side by 0. Because if n was less than 0, then it was negative, and we have already handled the negative values. And for positive values, like we can now apply induction. I hope you guys understand the high level idea of what I'm trying to say. So we can't apply to prove this. We have to be a bit smart while applying induction, as n is now unbounded on both the ends. So what we actually do is first assume. So we'll actually divide this into two cases, where the case one is. So we divide it into two cases. And like two cases is first case is n is less than 0. And in this case, it can be seen that in this case, LHS is less than 0, whereas RHS is 2 to the power n is greater than 0. And hence, the inequality goes. So we know that so we have proven the case one where n was less than 0, that this holds. And now the only remaining case is for the greater than equal to 0 value of n. For n is greater than equal to 0 case, now we have n is greater than equal to 0. So n is 0, 1, 2, 3, and can go until infinity. So now we can apply induction. N equal to 0 will be the base case, and you can see that base case holds because n equal to 0 is 0, 2 to the power 0 is 1. So 0 is less than 1. And now induction can be applied. Can be shown that the equality holds. Okay, or maybe just. So I hope everyone understands why I divided into two cases. So note that sometimes it might be possible for n less than 0. This sort of direct argument is not possible. But now we can apply induction in this case also. Like induction can be applied. What I'm trying to say is induction can be applied only when one side of our inductive variable is bounded and other side is unbounded. So if both ends are unbounded, we divide it into two cases. One case here also, like in this case, n can from minus infinity to minus 1. So again, like there is a one side is bounded by -1, even though other side is unbounded. Similarly, here also one side is bounded, but other side is unbounded. And in these two cases separately, also we could have applied induction. In this case, like I don't know what the if inductive argument will hold exactly for this sort of inequality, but maybe for some other question, this n is less than equal to 0 case would also be solved using induction. I hope this is clear to everyone. If so, maybe move on. So option D is true, C is true, B is false. So only option B is incorrect. So option B is the correct answer. So one thing I would like to mention in today's session, uh, rather than just knowing the answer, like what's the truth, whether the answer is true, false, or true, the nuances which I'm telling you guys are more important in my opinion. Because in general, whenever you are proving stuff and something, induction will be used a lot, and these nuances will come into play. So these types of settings that when both ends of the variable are unbounded, then we can do using this. And similar kind of thing, like here in Pigeonhole principle, I described that we need to prove a lower bound also as well as an upper bound. So things like this are also very important. Like these are in fact more important than the actual answers to these problems. So please pay attention to these proofs also, which I'm telling you. So yeah. Now let's come to the fifth question. Fifth question says that is the given inequality true? The inequality says that 2 to the n is less than n factorial for all n belonging to the set of natural numbers. Again, I believe this is somewhat straightforward. This question directly is straightforward because it can be seen that for n equal to 1, this fails to hold. Like this side becomes 2, whereas the right side becomes 1. And it is false. And why is this false? As it does not hold for n equals to 1. For n equals to 1, this side is true, whereas this side is 1. So this inequality is false. But once again, let's just see what. So we know that for this question, the correct answer is false. But let's just delve deeper into this. So when we put n equals to 1, this side was true, this side was 1. So left side, this inequality was false. Similarly, for n equal to 2, this side will be 4 and this side will be 2. Again, the inequality will be false. For n equal to 3, this will be 8. 2 to the power 3 is 8, whereas 3 factorial is 6. So again, this will be false. For n equal to 4, though, for n equal to 4, this will be 2 to the power 4, which will be 16. And this will be 4 factorial, which is 24. So this this holds for n equals to 4 at least. This inequality holds for n equal to 4. And now actually using induction, again mathematical induction, taking the base case as n equals to 4, you can prove that it holds for all n greater than equal to 4. Right. So again, using an inductive argument, it can be shown that uh, it holds for n greater than. I would suggest that you guys also try this out yourself. That inequality hold for n is greater than. Maybe we can see one of such proofs if we have time at the end of the session. But I don't think we'll be having time. But yeah, otherwise you should definitely like be comfortable with proving these sorts of settings using induction. because this will be very helpful when trying to prove things. Okay, so now maybe move on to the fifth question. Fifth question says that, let's just put this side. So a fifth question says that a black colored opaque bag contains 15 red gloves and 15 green gloves. Krishna takes out one glove at random each time. How many gloves must he take out to be sure that he has at least two red gloves? So what do you guys think? Like there are 15 red gloves and 15 green gloves, and Krishna takes out one glove at random each time. How many gloves must he take out to be sure that he has at least two red gloves? So there are total 30 gloves, 15 red, 15 green. So yeah, so Akansha says 17. So yes, Akansha, so that is the correct answer. Answer is 17. But once again, we'll just see. I'll just write out like why is this the case. So suppose we take 17 gloves. So the intuition behind it is that in the worst setting, what can happen is in the first 15 tries, all the green gloves are picked by Krishna. And now only red gloves are remaining. And so as soon as he picks two red gloves, he can be sure that those two are red. So when you have picked a total of 17 gloves, you can be sure that you have picked at least two red gloves. So again, what we'll actually need to show is an upper bound, like that we need to show that if 17 gloves, we pick 17 gloves, we are sure that we'll always pick at least two red gloves. But we also need to show a lower bound that if we pick 16 gloves, then it is not possible to uh, always obtain at least two red gloves. I believe this is the trivial. Suppose we take 17 gloves, then number of green gloves picked is less than equal to 50. And since number of green gloves, and since we know that number of green gloves plus number of red gloves is actually equal to 17, so number of red gloves will be just greater than equal to. This means that number of red gloves greater than equal. So if we take 17 gloves and less than equal to 15 of them are green, then just by straightforward inequality, we can say that the number of red gloves will be greater than equal to. And now this is an upper bound. Like if we pick 70 gloves, we are sure that at least two will be available. But we also need to show that in less than 17, it won't be. So this might seem trivial, like for at least these problems, this sort of lower bound, setting lower bound. But in a lot of problems, finding this lower bound is actually very hard. For this, it is trivial, but there exists a lot of problems where you can find an upper bound, but really you have no idea about what the lower bound should be. So that's why, although we are discussing simpler problems, but we should be comfortable with this lower bound idea also. Show that 17 is the lowest possible answer. Suppose 17 was not the lowest. Suppose we pick 16 low. Then it is possible that the that there are 15 green and only one red glove picked. So there can be an example in 16 gloves where 15 are green and one is red. So this case fails. So our condition will not always be satisfied if we pick 16,000. So 17 is the minimum possible. 17 is the minimum possible. I hope this somewhat makes sense. And now maybe we can just so this is not another question. This is just an extension of this question. Suppose instead of uh, ensuring that we have at least two red gloves, suppose the question was instead how many gloves must he take out to be sure that he has at least two gloves of the same color. And I have already written the answer also for this. But the main idea, I hope everyone gets that. Uh, in the initial question, the question asked that we should pick two gloves of the red color. And then the answer was very big, which was 17. But suppose I just change the question a little bit and I say that the two gloves should be of the same color. So the two gloves can be red colored or green colored. Then the answer comes down dramatically to just three gloves. And why is this the case? Because uh, if we take out red and green glove, then whatever the third glove is, uh, we'll just get a pair of the same color, right? Because it was red, then it would be paired with this red. If the third glove was green, it would be paired with this green. So if we just want to find out the number of gloves to be picked such that at least two gloves are of the same color, not of the red color, but they can be of like, same color can be green also. In that case, the answer comes down dramatically from 17 to just 3. Yeah, just I just want you guys to appreciate the nuances, like just changing like from one color to like from being strict about the color to just really like, relaxing this condition and just saying that any color, but it should be the same color. The answer can change very dramatically. Okay, so I hope it's clear to everyone. If it is not, I will encourage you guys to ask me in chat and I'll try to explain it again. Otherwise, maybe we can move on to the next question. So the sixth question says that, okay, so this is again an inequality based question. For positive integer n, 10 raised to the power n minus 2 is greater than 81n. If so, effectively the question is asking us when, for what values of n does this inequality hold? That 10 to the power n minus 2 is greater than 81n. So we also have options for this question, but any guesses? Not just guesses, I would assume that you guys should be able to answer this. What should be the correct answer in this question? 10 to the power n minus 2 is greater than or equal to 81. Okay, so Suvarna is saying that A option is correct, that n is greater than 5. Okay, like it holds for n is greater than 5, Suvarna, but let's just say if it was single option correct, then like actually what I'm trying to say is it also holds for n equals to 5. Like not just n greater than 5, but also equal to 5. So the correct answer is option D. But I guess you maybe assume that this question is multiple choice, so you also said option A is correct. But if this was like, let's say, a single choice correct question, then you have to select the most appropriate choice, right? And then this is a more tighter bound that n is greater than equal to 5, then n greater than 5. So it doesn't matter. I hope you get the high level idea that we'll show why this is correct. But yeah, first let me write down the answer. And how do we come to this answer? Now we'll show. So the inequality given to us is this, that 10 to the power n minus 2 is greater than 81n, right? Uh, so first, we you can actually see that putting n equals to 1, we'll have something like 10 raised to the power minus 1, which will be less than 81n. Similarly, for n equal to 2 also, n equal to 3 also, this will be smaller. And for n equal to 4 also, this will be smaller. Because 10, for n equal to 4, this will be 100. 10 raised to the power 2 is 100, whereas this will be more than 100. But for n equals to 5, this will be like 10 raised to the power 5 minus 2, which is 1000. And this will only be 450. So then this inequality starts to hold true. So first, it can be easily seen that it can be easily checked that maybe I should move the fourth question to the next page. Can be easily checked that the inequality does not hold for n equals to 1 to 3. So for n equals to 1 to 3, for this inequality does not hold. But it holds for n equals to 5, right? And we know that it holds for n equals to 5. And now we will show that this holds for n greater than 5 also, like not just for 5, but it holds for 6, 7, 8, 9, 10, for all positive integers n. And for this, we will be using induction to show that it holds for n greater than equal to 5. We use induction. And maybe for this question, so for previous questions, like I have just left the proof for you guys to figure out yourself, the inductive proofs. Maybe I can discuss one such proof in this question. Like, let's just try to prove this fully. Let's just try to prove this question fully. So first of all, what will be the base case for us? Or maybe let's just first write down the inductive argument. The inductive claim will be something like pi and 10 raised to the power I minus 2 is greater than 81i. So this will be our inductive claim, this multiplication. And this should hold true for I greater than equal to 5. Right? And what do we do in the whenever we use induction? So first of all, we do the base case. So base case will be I equals to 5 is our base case. So base case is I equals to 5. So 10 raised to the power 5 minus 2 will be just 1000. So 10 raised to the power 5 minus 2 is greater than 81 times 5. Hence, the base case holds. And now we'll need to show that if pi is true, so we now need to show inductive case that if pi is true, then pi plus 1 is true. So what does this mean? That pi implies p of I plus 1. That if pi was true, then p of I plus 1 will also be true. So we actually need to show that if 10 raised to the power I minus 2 is greater than 81i, then 10 raised to the power I plus 1 minus 2 should be greater than 81 times I plus 1. Right? And how can we do this? So let's just, we need to prove this thing, right? That pi is true, then pi plus 1 is true. So let's just see, we can write the RHS, the LHS, which is 10 raised to the power n minus 2 as like, so this was 10 raised to the power, okay. Yeah, I should zoom in for you guys. what we needed to find was what we need to prove was p of I plus 1. We know that p of I is true. We need to prove p of I plus 1. So when we use p of I plus 1, the LHS will be 10 raised to the power I plus 1 minus 2. And we need to show that this is greater than this part. We can't assume that it is greater than 81 times I plus 1. We need to show. So what will be the LHS? First of all, when we try to prove for I plus 1, it will be 10 raised to the power I plus 1 minus 2. And this can be written as nothing but 10 times. So, okay, maybe I should write like this, that first of all, I should simplify this. This is 10 raised to the power I plus 1 minus 2 is nothing but I minus 1. And this is nothing but 10 times 10 raised to the power I minus 2. And why did I convert it into this I minus 2 form? Because I know that this I minus 2 now, I can use this claim. Because I know that Pi is true. So I know 10 to the power I minus 2 is greater than equal to 81i. So I can replace this and say that this is greater than 81i. Right? So I can say that this is greater than 10 times this part, which is greater than 81i. So something like this will work. This times 81 times I. Okay. But this is not what we needed to show, right? We need to show that this should be greater than 81 times I plus 1. Right? And how can we show this now? So we can, so 81 times I plus 1 can be written as something like 81 I plus 81, right? For I plus 1, this will be like 81 times I plus 1, which will be 81 I plus 81. So I try to write it in that form only, that I take out 181i. So I try to write it as, I write this as 9 plus 1 times 81 times I. So I write this 10 as 9 plus 1. And by what is my reasoning for this? So that 181, this 81i comes out when I distribute this. And this will be nothing but 9 times 81 times I plus 81 times I. Right. And now like we have at least one part of the RHS. Like this should be 81 times I plus 1 for Pi plus 1. And we have the 81 I part. Now we need just a plus 81 part. So we just need to show that this is greater than 81 and we will be done. So I hope everyone understands. So we know that this 9 times 81 times I will be greater than 81, right? Because 81 times 9i and I is already greater than equal to 5. So this will be greater than 81. So this whole expression will be greater than 81 plus 81 times I. And this is nothing but 81 times I plus 1. 81 times I plus 1. Okay. Maybe I should just, yeah, so that everything comes in a single line. Yes. So this is how, so effectively through the series of inequalities, we have shown that 10 raised to the power I plus 1 minus 2 is, this is greater than 81 times I plus 1. So what this implies is, maybe I should just write this down. Is greater than 81 times I plus 1. And this means that, so this was indeed P of I plus 1, right? And hence P of I plus 1 holds. this was actually indeed the statement of P of I plus 1. So P of I plus 1 holds. And note that where did we use the state fact that Pi was true? Like we somewhere used because that Pi was true, right? Because only Pi was true, then Pi plus 1 was holding. We use that fact here, where we said that this 10 raised to the power 81, like 10 raised to the power I minus 2 can be written as like can is greater than 81i. Like we replace this 10 to the power I minus 2 by 81i because of Pi. So Pi implies Pi plus 1 and P of 5 is true. Like we know Pi implies Pi plus 1 and P of 5 is true. And because of these two arguments, hence by induction, uh, the inequality holds for n greater than equal to 5. I hope this makes sense. Like this is how we actually write the proof. And now maybe we can move on to the seventh question. And the seventh question just says that um, first of all, so this is why like n greater than equal to 5 option D is the correct answer. Seventh question says that a basket containing 60 walnuts was kept in the veranda. 10 squirrels randomly came and took away some walnuts. So after some time, the gardener found the basket empty. Which of the following conclusions is always true for the given situation? So we are given four conclusions and we want to figure out which of these will always hold. Like at least one squirrel went back with at most 6 walnuts. At most one squirrel went back with at least 6 walnuts. At least one squirrel went back with at least 6 walnuts. At most one squirrel went back with at most six. So maybe this can be multiple choice correct. So I would like you guys to like first try this out. So what should be the would you like to guess, Suvarn Lakshmi, what should be the correct answer for this? Okay, so so Suvarna is saying that A should be the correct answer. At least one squirrel went back with at most 6 walnuts. So yeah, I think A is correct, but like this is a multiple choice question, Suvarna. So actually, not just A is correct, but the options A and C both will be correct. That at least one squirrel went back with at least 6 walnuts, and at least one squirrel went back with at most 6 walnuts. And like why will this both of these claims will be true? So maybe we can just figure this out. So let's just assume that the squirrels assume the 10 squirrels took x1, x2, or maybe do something like this. Assume the ith squirrel took xi number of walnuts. So there were 10 squirrels. Let's assume so I is from 1 to 10. Let us assume that ith squirrel took xi number of walnuts. So we know that after some the basket was finally empty. So we know that the number of walnuts that the squirrels took together was 60. So what we know that x1 plus x2 till x10 is actually equal to 60. Like, all these squirrels together took 60 walnuts. So now what we can say by this, like we know that x1 x10 is actually equal to 60. Now one thing which we can observe is assume, like let us assume that like out of these x1 till x10, like one of these will be the maximum, right? uh, so let us assume that something like xj is the maximum. Okay, assume xj equals to max of x1, x2, and so on till x10. So these are 10 numbers. Out of these 10 numbers, let's say the jth number is the maximum, right? Out of these 10 numbers. And similarly, xk is the minimum. Maybe I should copy this. That xj is the maximum, xk is the minimum of these 10 numbers. So what can we say about these values of xj's and xk's now? This is what we'll be figuring out. So we know that xj will be, since xj is actually the maximum out of all of these, so it will be greater than equal to each of these, right? Xj will be greater than equal to x1. It can be equal to x1, but it will be at least as large. Like x1 can't be more than xj because otherwise x1 would have been a maximum. So xj is greater than equal to x1, xj is greater than equal to x2, and so on till xj is greater than equal to x10. And what does this net us? We have these 10 inequalities. And if we add all of these 10 inequalities up, if we add these 10 inequalities, then we'll get that adding these 10 inequalities, we get, maybe I should write like this. What we'll get, so xj will occur 10 times. So this will be 10 times xj. And this will be greater than equal to x1 plus x2 plus x3 till x10. And we know that this sum is actually equal to 60. So 10 times xj will be greater than equal to 60. And what does this imply? This means that xj was greater than equal to 6. Okay. So we obtain that xj is greater than equal to 6. What does this mean? Xj was at just the maximum over like all the like first squirrel took some walnuts, second squirrel took some other number of walnuts till 10 squirrel. And now xj was the maximum over all of these, which means that xj denotes like the jth squirrel, the number of walnuts that this jth squirrel took. Right? Xj just denotes the number of walnuts that the jth squirrel took. And now we have shown that this is actually greater than equal to 6. So we know that jth squirrel took at least 6 walnuts. And so like at least one squirrel went back with at least 6 walnuts. And who was the squirrel? This was the jth squirrel. Like there can be more squirrels with at least 6 walnuts, but at least there was one, which was this jth squirrel. There can be more squirrels which took greater than equal to 6 walnuts, but we now know that there was at least one. Hence, at least one squirrel went back with at least 6 walnuts. Now, similarly, first we showed that xj is greater than equal to 6. Now we know that xk is the minimum over these. So this is the number of walnuts taken by the kth squirrel, and it is the minimum over all these quantities. And now we somewhat know that like these inequalities will be reversed. Like xk will be less than equal to x1, xk will be less than equal to x2, till xk will be less than equal to x10. And from that, we'll get that 10 times xk is less than equal to 60. And from that, we'll get that xk is less than equal to 6. So following the same things, but just with the inequalities reversed, we'll get that xk is actually less than equal to 6. And if xk is less than equal to 6, then this means that the kth squirrel took at most 6 walnuts, not more than 6. And this is what option A says, right? That at least one squirrel went back with at most 6 walnuts. Similarly, we can get xk is less than equal to 6, and hence at least one squirrel went back with at most 6 walnuts. So hence options A, C are correct. Right. I hope this makes sense. If you have any doubts, you can ask in chat. Otherwise, I assume that it's clear to you. Okay. So now we come to the eighth question. So eighth question says that state whether the following statement is true or false. So the eighth question is like saying for all n belonging to n, 6 to the power n minus 1 is a multiple of 5. So we need to say whether the statement is true or false. So actually, like, let me just tell you, like, this is not too hard, but this statement will also be true. Like for n equal to 1, we can just see that it's will be 6 minus 1, which is 5. Then 6 square minus for n equal to 2, it will be 6 square minus 1, which will be something like 36 minus 1, which will again be 5, which again will be divisible by 5, and so on. So, and if this is true, like we need to show this for all n. We can't just give examples like it's true for n equal to 1 or 2. So we need to prove it by induction. Can we prove by induction? And how do we prove this? So our claim will be the inductive claim will be like, let's just assume Pn will be that 6 to the power n minus 1 is divisible by 5. So note that being a multiple of 5 and being divisible by 5 are the same thing. And now we have a base case. The base case will be P1 is true. Like P of 1 will be the base case since we have for all natural numbers start from 1. So base case will be P of 1, and this will be true because putting n equal to 1, we get 6 to the power 1 minus 1, which is like 6 to the power 1 minus 1 is equal to 5. Maybe I should write this like what the question asks. Which is a multiple of 5. Right. So we have the base case. Now we'll need to show the inductive case, right? So first of all, we know that Pn is this. We know that Pn was this, that 6 to the power n is a multiple of 5. So what will be Pn plus 1 now? P of n plus 1 is what we'll actually need to show. So we'll need to show that if Pn is true, that if 6 to the power n minus 1 is a multiple of 5, then 6 to the power n plus 1 minus 1 is a multiple of 5. Right? And now, sorry for that. So we need to show that P of n implies P of n plus 1. So this is something which we'll need to show using induction. This is what is induction, right? So we'll assume that this is true, and we'll try to show that this is also true. So first of all, let's come to this expression. We need to show that this expression 6 to the power n plus 1 minus 1 is a multiple of 5. So let's just observe this expression, what this actually is. So this is 6 to the power n plus 1 minus 5. And this can be just written as 6 to the power n plus 1 can just be written as 6 times 6 to the power n, like, and minus 1. I just took 1 6 out of this and wrote it as 6 times 6 to the power n and minus 1. And now this 6 can be written as nothing but 5 plus 1, a similar trick which we employed earlier. So this will be nothing but 5 plus 1 times 6 to the power n minus of 1. And this will be just equal to 5 times, okay, 5 times 6 to the power n. So I just open these parentheses, 5 times 6 to the power n plus 6 to the power n minus of 1. And note that now if I look at this quantity, this 6 to the power n minus 1, I can say that this is a multiple of 5. And why can I say this? Because this was my P of n. Like I assume that P of n is true, and now I was showing P of n plus 1 is true. So in this inductive hypothesis, we have assumed that P of n is true. I know that 6 to the power n minus 1 is a multiple of 5. And note that this is also a multiple of 5. And why is this a multiple of 5? Because it just has a factor of 5 in it directly. So what this actually means is that this term is a multiple of the whole term 6 to the power n minus, okay, this should be 1. This whole term 6 to the power n plus 1 minus 1 can just be written down as a sum of two terms, both of which are multiple of 5. This is a multiple of 5 we can see directly, and this is a multiple of 5 by our inductive hypothesis. So this term is the sum of two multiples of 5, and so like sum of two multiples of 5 is also a multiple of 5, right? So this is a multiple of 5 as 5 into 6 to the power n is trivially a multiple of 5, and 6 to the power n minus 1 is a multiple of 5 as P of n is true. So what this actually means is like this term is a multiple of 5, and so P of n plus 1 is true. Hence, P of n plus 1 is true if P of n is true. So we have shown that P of n implies P of n plus 1, and we had also shown the base case. So by induction, we can say that P of n is true for n greater than equal to 1. So I hope this makes sense and gives you an idea of how to proceed using induction. So like here, this was a good idea that we wrote down the 6 as 5 plus 1, and then we use the inductive argument. So these are some techniques which you can employ in proofs. So yeah. Now we can move on to the ninth question. Ninth question says that Madhu, Anushka, and Prasad bought a white chocolate consisting of n blocks. The chocolate is distributed equally among all the three members. Madhur likes to enjoy the chocolate, having it one block at a time. How many total breaks does Madhu require to finish her share of chocolate? So like a chocolate has n blocks and chocolate is distributed equally among all the three members. So the part which Madhu gets, Madhu will take one block at a time. So how many total breaks does she require to finish her share of chocolate? So any guesses? I believe this is a not too difficult question. This is a straightforward question. Uh, would you like to guess, Suvan Lakshmi? Okay, maybe I could just write down it's too complicated of a question anyways. So we know that the chocolate had n blocks and it was distributed equally among all the three members. So this means since the chocolate was distributed equally. Okay, so is my screen not visible, Suvarna Lakshmi? You're saying question, you are unable to see the question. Is my screen not visible right now? Maybe I can reshare my screen if that's the case. I've reshared now. So maybe I should just type down in the meanwhile. So chocolate was distributed equally, and the chocolate initially consisted of n blocks. So Madhu will get chocolate consisting of n by will get a part consisting of n by 3 blocks. So Madhu will get a part consisting of only n by 3 blocks, but she likes to eat it one block at a time. So even though the initial chocolate was, let's say, cons- consisting of these n by 3 blocks, these were joined together. And now Madhur will need to break these one at a time uh, to finish her chocolate, right? So now, how many blocks will she need? Let's just see what an example chocolate will look like. So let's just assume that Madhu has a part which has like, let's just see, like Madhu has, let's assume that 3 blocks. So how will this chocolate look like? If Madhu had a part which consisted of 3 blocks, then this chocolate will look something like this, right? That there are 3 blocks, and these are the 3 blocks for the chocolate. Like one block, then there's the separator, then the second block, and then there's this third block, right? So this part denotes the chocolate actually. I'm trying to show here. And now if Madhu needs to eat this chocolate one block by block, she'll first need to break this part apart so that she can eat the first block. And then when only 2 blocks are remaining, she'll again need to break off this part so that she can eat these 2 blocks individually. So when we had 3 blocks, Madhu only needed 2 breaks. 2 breaks were one here and one here. So to eat this chocolate one block at a time, Madhu needs 2 breaks. Right. So similarly, for n by 3 blocks, she'll require n by 3 minus 1 breaks. And yeah, so this is the answer. Hence, option D is correct. So very trivial question, not too hard. Like someone just okay, so okay. So Suvarna, is my screen not visible right now? or is it visible to you? Like I have instead of like me saying the question aloud, like you can just see it on the screen. Like, I have been sharing my screen. Uh, no, so like uh, so Varna, so that's what I'm saying. Like n minus one breaks are needed for a chocolate of length n, but Madhu has only n by three length chocolate because initial chocolate had n blocks, but it was distributed among three people. So each of them got only n by three blocks. And so, like for a chocolate of length n by three, now for a chocolate of length n, you needed n minus one breaks. Now, chocolate of length n by three, you will need n minus three minus one breaks. That's why option D is correct. So just like not too hard of a question, but just need to take care a bit like of not doing any silly mistakes in this. But otherwise, this is a straightforward question. So, yeah. Okay, so now we move on to the last question of the day, and this is a somewhat of a challenging question. Like you must have observed, like almost at the end of every session, I give one very challenging question. Like all these questions, the previous questions are generally not too hard, but usually the last one or last two questions which I give are uh, pretty hard. These types of questions won't be asked all obviously in the NPTEL exam or quizzes, but these uh, enhance your like thinking capabilities, in my opinion. That's why I like to give at least one question in every such session. So the last question says that given any natural number n, prove that there always exists a pair of distinct natural numbers a comma b such that 2 to the power 2 to the power a minus 2 to the power 2 to the power b is divisible by n. So this will be a bit of a difficult question for you to attend, but I would still like you to at least think about it for like 5 minutes, let's say. So like I'll be muting myself for let's say 5 minutes. You can try it out and just like you can just think aloud or any idea which you think can work for this question possibly. You can type out in chat. So I'll be muting myself for 5 minutes, and after that, we'll try to solve this question. Till then, you can try. You should think about it yourself and present, like write any idea if it comes to you in chat. So yeah, I'll be muting myself now. Just a hint, this question may seem very like this function, like this term may seem very daunting or like very some special trick is required. But believe me, this question is actually like it just involves very simple reasoning, just pigeonhole principle. So that's a hint. Like, do not think in too much complexity for this question. The final answer will be very simple. Okay, so you're saying no idea. So maybe we can just maybe I can then just send the solution. But believe me, like when you see the solution, like you'll think that this was very trivial. Not trivial, but like but something which could have been done. So let us okay, maybe I should. Yeah. So just consider this function, like consider the function f of x. So consider this function, like f of x equals to 2 raised to the power 2 raised to the power x. See, like this value is just equal to f of a, and this value is just equal to f of b then, right? So this is the function f of x equal to 2 raised to the power 2 raised to the power x. So now what we just need to show is then we need to show that there exists distinct a comma b such that f of a minus f of b is divisible by n, right? We just need like f of a is this number 2 to the power 2 to the power a, f of b is this number 2 to the power 2 to the power b, and their difference is what we need to show is divisible by n. So f of a minus f of b is divisible by n. Only this is what we need to show. So now just consider, okay, maybe I should just put this whole question on the next page. Yeah. And note that a very high level idea which I want to give you is, so suppose f of a minus f of b is divisible by n. What does this mean? If f of a minus f of b is divisible by n, then this means that on division by n, both f of a and f of b leave the same remainder. Only then will their difference be divisible by n. So what I'm saying is this number, this 2 to the power 2 to the power a, and this 2 to the power 2 to the power b, both should leave the same remainder on division by n. Only then will their difference be actually be divisible by n. So this is the high level idea, and now we'll try to find two such a and b such that f of a and f of b will leave a remainder of, will leave the same remainder when divided by n. And how do we go about this? Again, we can sort of use the pigeonhole principle. So just take the set of numbers, take the set of numbers. So just consider this set of numbers, like f of 1. So f of 1 will be the number 2 raised to the power 2 raised to the power 1. Similarly, f of 2, f of 3, and till f of n plus 1. So consider these n plus 1 numbers, f of 1, f of 2 till f of n plus 1, right? Since these are n plus 1 numbers, uh, we you can easily see that all these n plus 1 are also distinct numbers, because like f of 1, this is an increasing function. So all of these are distinct numbers. It can be seen that S consists of n plus 1 distinct numbers, right? And what do we know? We know that, and what I'm trying to show, and what I'll show is there exists a pair of numbers out of these which leave the same remainder when divided by n. So out of these, there will exist a pair of numbers which will leave the same remainder when divided by n. And so their difference will be divisible by n. And actually, this is not too hard to show because this is just an application of pigeonhole principle. So we know that any natural number when divided by n can only leave remainder or maybe leaves remainder equal to 0, 1, 2 till n minus 1. So whenever a number is divided by n, the remainder can only be one value out of 0, 1, 2, 3 till n minus 1, right? The remainder is always between 0 and n minus 1. And note that these are n, so there are actually n possible remainders only. So there are only n possible remainders on division by n. So like these are n possible numbers. You can see 0 till n minus 1 are n possible numbers. So there are n possible remainders when we divide something by n. But now note that these numbers, let us say we divide all of these numbers by n, and let's look at their remainders. So now look at the remainders when numbers of the set S are divided by n. Let us call the remainders R1, R2 till Rn plus 1. So these are n plus 1 numbers. When all of these are divided by n, like when f1 is divided by n, let's say it leaves remainder R1. When f2 is divided, it leaves remainder R2. And when fn is divided, let's call it Rn plus 1. So there are n plus 1 possible remainders here, R1 till Rn plus 1. Right? They leave n plus 1 remainders. But we know that the only possible remainders are n. Like actually only n possible remainders are possible on division by n. But these are n plus 1 numbers, so they leave n plus 1 remainders. So what does this mean? By pigeonhole principle, this effectively means that there is at least one remainder, like which is common to two numbers. Like there exist two numbers, both of which leave the in this set there exist two numbers, both of which leave the same remainder on division by n. And if that's the case, then I'm claiming that we have solved the problem. Because let's say there are two numbers fa and fb, such that they leave the same remainder, then their difference fa minus fb will be divisible by n. And this is what we needed to show, that there exists a pair of distinct natural numbers such that this is divisible by n. So this is the high level idea which by which we are able to show that uh, this holds true. Maybe I should just write it down what I have just said so that it's easier for you to grasp and everyone also to look at it later if they're looking at the recording. So what effectively we can do is, so we can think of the possible remainders 0, 1, 2 till n minus 1 as n wholes, and the numbers R1, R2 till Rn plus 1 as n plus 1 pigeons. So there are n wholes and there are n plus 1 pigeons. So what does this mean? By pigeonhole principle, there exist two numbers or maybe let's say uh, there will exist two remainders, like okay, two numbers, let's say RA and RB, two remainders RA and RB, which will be equal to each other. Or maybe which will be equal. This is not sufficient. And why is this the case? So there are only n holes, there are n plus 1 pigeons. So at least one hole out of these 0, 2, and minus 1 will contain two of these remainders. And so like two of these remainders, it contains two of the remainders, which means both these remainders are equal. So let's say these two are just RA and RB, and they will be actually equal. So what this actually means is, so we get two numbers. We get that there exist two numbers, FA and FB, from set S, such that they leave the same remainder on division by n. And what does this mean? Hence, FA minus FB is divisible by n. So we have actually proved that FA minus FB is divisible by n. Hence, there always exists a pair of numbers such that FA minus FB is divisible by n. So I hope the high level idea is clear. We took a function, we took it different n plus 1 values, and then we took all the possible remainders, and we showed by pigeonhole principle that at least one remainder will occur twice. And as soon as one remainder occurs twice, then then the difference of those two numbers, FA and FB, will be divisible. So this is the high level idea. In writing, it may look long, but the high level idea is very simple. Just look at the possible remainders of n plus 1 values. One of the remainders will occur twice, and then the difference will be divisible by n. So that's why I was saying that this question, even though it looks complicated, this function looks very complicated, but the question was very simple and very beautiful. So similarly, like this question can be extended arbitrarily, right? I could have written instead of 2 to the power 2 to the power x, I could have written something like 2 to the power 2 to the power 2 to the power x. I could have had a multiple tower of 2s. And then still my argument would have been the same, that I took f1 till fn plus 1. And then I would have shown that using pigeonhole principle that the remainder will be, there will be at least one remainder which occurs twice. And so difference will be divisible. So this is a very beautiful question. And I think this also gets asked a lot in interviews. So yeah, so this is a bit tricky question, but the trick is very simple. So yeah, I just I would like you to look at this question again after this session so that you can assimilate that whatever happened in this, whatever we discussed here. So, yeah. Okay, then so this was the last question which I had prepared for the day. And yeah, I believe we are right on time. The time is exactly 8 p.m. right now. So Suvarna Lakshmi, do you have any doubts? Okay, Suvarna is typing something into chat. Okay, so more questions for practice purposes. So I believe, Suvarna, I believe some questions are already being discussed during the lectures, right? In the lectures also, when Sir teaches theory, he also discusses some questions. And I also give and we discuss in these sessions also at least 10 questions. I believe this much material is sufficient for the quiz purposes. I don't think you require anything more. I from my end, I at least always try, like even in these tutorials, you can see that I give some extra questions like which are a bit more challenging. And I think like if you are able to solve these types of questions, you don't need any more practice. Like okay, for end exam. So maybe I can see if I can find a bit more questions. I won't discuss them during the problem solving sessions, obviously, because we only have limited time. But in the Google Drive where we upload all this stuff, uh, all these problem statements and all, maybe I can upload some extra questions there. So yeah, I cannot guarantee that the solutions will also be attached because I'll have to type in the solutions that can take a bit of my time, but at least I can provide questions. And like one thing more, like I just want to point out that if you want extra questions, you can just always look at some discrete mathematics books. Like there are a lot of good books available for discrete maths. Even NPTEL course would have recommended some books. So you can solve the solved exercises for those books or just the back exercises. And this should be sufficient for the exam preparation or in general also. Okay, sure. So, do you have any other doubts, Suvarna? If not, maybe we can close the session then since we are already out of time. If you have doubts, then okay, so you have no doubts. So nice. So once again, I thanks for joining and hopefully I'll see you next week also, same timing, Monday, 6 to 8 p.m. So till then, goodbye. You can leave the session now. I'll stop the meeting. So thanks for joining again. Bye bye.